Okay, so we are recording the section, so we will go to this last talk of this morning scientific program for the first day. So it's a pleasure to have Professor René Montenegro as our invited speaker, next invited speaker from Universidade Federal de Pernambuco in Brazil. And I would like to thank René for accepting our invitation to contribute to the scientific program of this meeting. Thank you, Professor René. So you have the talk now.
Good morning for all. First, I would like to thank the Professor Marcelo Lira, Professora Socorro, Jordana, e Luana, the organizing committee, to organize this workshop. For here, I will talk about the ground state phase diagram and thermodynamics of coupled time machines. This work was recently published and was done with Aglanio and Professor Maurício Coutinho. I will talk first about the model and methods. In the sequence, I will show you the magnetization curves and phase diagram. And after, I will talk about the low energy excitation, the susceptibility, and I will end talking about the closing of the 1/3 plateau at zero temperature. The model is this, the coupled time machine. In its side, we have a spin 1/2, and there are two couplets, one an intra-trimer and the other G2 intertrimer. We have a Heisenberg Hamiltonian in a magnetic field. We have used the DMRG method, our own code, and the Monte Carlo results was obtained with the ALPS library. The magnetization curves are here. In the upper panel, we have the four positive values of the J2 coupling, and in the bottom panel, we have four negative values of the J2 coupling. For positive values, the Leibniz theorem applies, and in zero magnetic field, we have finite magnetization and a gap that produces a magnetization plateau in a magnetic field. In the negative range of J2, of the D2 parameter, the Leibniz, we cannot apply the Leibniz theorem. The magnetization is null, is zero, in zero magnetic field. But as we increase the magnetic field, we reach the 1/3 plateau also. There are also little steps just after and one of the extreme points of the 1/3 plateau. These are associated with edge states for positive values of J, and for negative values of J, these steps, these associated with edge states, are found only near the full polarized plateau. Here is the full phase diagram of the model. The 1/3 plateau exists here in this range, and For negative values of J, we have a gapless liquid phase. In zero magnetic field, you have a singlet state for J negative, and a ferrimagnetic state for positive values of J. But if we go to values of J more negative values of J, the ordering of the unit cell changes. We have down to this value a ferrimagnetic order, but if we continue to reduce the value of J, here we have a ferromagnetic polarization of the unit cell spins. All the gapless phase is a Luttinger liquid phase. And we have here the full polarized plateau that's also gapped. Low energy excitations. We will study the low energy excitations from the 1/3 plateau first, and second from the singlet state here. From the 1/3 plateau, we have bulk excitations. We have 3 coupled spin 1/2 in each unit cell, and we will have 3 excitations that we can obtain from these formulas here. The 2 of them are have a dispersion or expressive, and one of them is near flat. As we decrease the value of J from J equal to 1, these excitation here, a ferromagnetic excitation, becomes less dispersive. And here we have the coupled chain limit, the coupled time limit. All the excitations become flat. For negative values of J, this excitation is unstable, and it's associated with that we have in a range of J values that the ground state in zero magnetic field is the singlet state. We also have a ferromagnetic excitation that is nearly flat for all values of J, and an anti-ferromagnetic excitation associated with this gap here, and this value of magnetic field here and here, that becomes less dispersive, but for all values of J, it is dispersive except the couplet chain limit. Another excitation, as I talked, is the edge excitation. This little step near the plateaus. The first is near the 1/3 plateau, the second near the ferromagnetic plateau. These edge excitations are associated with 2 types of ground states. One of them is associated to the geometrical couplings in the system, and the other can be of geometrical nature, but also to the interactions in the system. The first, the edge excitation from the 1/3 plateau, exists down to some value here that is 0.0 6. Below this, the edge excitation disappears, and we have bulky excitations. Here, these kind of edge, we have studied a similar chain, ferromagnetic chain, in another paper, and we can associate this edge excitation to the interactions in the system, but this excitation also has a geometrical nature too. The excitation near the ferromagnetic plateau, this is purely of geometrical nature due to, if you take here the lattice, we will have a site here coupled antiferromagnetically with his neighbor. And if we lower the magnetic field from the ferromagnetic state, the flipped spin goes to the extreme of the chain. So due to this kind of local potential, a different local potential. So this edge state has a pure geometrical nature, contrary to this case of the 1/3 plateau. That's a mixed nature. Now we go to the excitations from the singlet state. To talk about it, we first analyze the correlations between the lattice spins, the spins in the chain. We show here the correlation function here, and along the B1 sides and along the A sides. We see here that we have an alternating pattern. Notice the -1 factor here. So we have an antiferromagnetic pattern on both chains, the A and on both chains, the A and B1 chains, an antiferromagnetic coupling. And if we consider the spin 1/2 chain, the correlation function in spin 1/2 chain, we see that the behavior in our case is similar to the spin 1/2 chain. We have 1/L decay of the correlation function, discarding this logarithmic factor here. So in the singlet phase, in that singlet state, the chain is organizing with this sketch. We sketch here the orientation of the short range orientation of the spins in the lattice. Each chain has an antiferromagnetic orientation of the spins, similar to and the decay of the correlation functions is similar to the spin 1/2 chain. So we have go further in this analogy and have tried to compare the excitations from the singlet state with the excitations of the spin 1/2 chain that has this dispersion relation here. But for a better comparison, we need to normalize the excitation with the parameter of the chain. Interestingly, is that the ground state has an alternation in the energy of the minimum with the wave vector. That is similar to the spin 1/2 chain. So we have a good comparison between the excitations and the correlations. of the spin 1/2 chain and of our chain, the couplet time machine. Now I will discuss the magnetic susceptibility and start from the magnetic susceptibility of the singlet state. And we start talking about the spin 1/2 chain susceptibility. It's interesting that this susceptibility, the the behavior of the magnetic susceptibility of the spin 1/2 chain was studied, and there is a closed formula for it. Here is the formula from this paper here. And this susceptibility is very interesting. He has an infinite slope here at t equal to 0, and has a finite value here at t equal to 0. This finite value is given by this number here. So we tried to compare our susceptibility results for the couplet time chain in the singlet phase with this formula here and this constant value of the susceptibility at t equal to 0. It's very difficult to take this value with numerical methods. Even with Bethe ansatz, it's difficult. It's another PRL. And even this value of this constant here, that's not universal. It's a very difficult task to take this zero temperature behavior of the susceptibility of spin 1/2 chain. But we cannot go to very little lower values of the temperature, but our results points to a direction that is that of that corresponds to this behavior of the spin 1/2 chain. Here we compare the susceptibility finite system of the linear chain. Here is this constant numerical value of the susceptibility. Here we are plotting the susceptibility at spin and the time chain for j equal to -1. And we notice that for st goes to 0, the susceptibility of the couplet timer presents an infinite slope also, and points to this constant value expected for the linear chain. Here we are studying the size dependence of the susceptibility. And here we change. Here we have the J2 equal to J1 minus J1, but in the other figure, we have changed this value of J1 for negative values too. This is the susceptibility for these values of J2. This is the J -1 that we have presented. And we are decreasing or increasing the value of the 2 up to 0. We note here that the susceptibility changes very much, but we can rescale it by J2 in order to have a behavior similar independent of the value of the J2 as T goes to 0, as near the new temperature. We notice that they point all to a region that is near the constant value of the susceptibility of the spin 1/2 chain. Né? This value here. Now we start the susceptibility of the ferrimagnetic phase for J, for positive values of J. And interesting, there is a compound that has a ferrimagnetic behavior, and we have tried to fit our results to the experimental results of this compound. The experimental results come from two papers. This paper here, the authors have studied the thermodynamics of the system, particularly the susceptibility, and the susceptibility, the product of the susceptibility by temperature has, in particular, the characteristic minimum of ferrimagnetic systems. And these experimental results in this paper, they have the same group have made neutron scattering experiments in the system and have obtained two excitations. They have two excitations here. They are very flat. They do not investigate. They did not have investigated these excitations in much more detail. The analysis requires, in our opinion, a more deeper investigation with a higher resolution of the energy, and in other energy scales, as we will talk briefly. First, we have tried to fit our results to the susceptibility of the susceptibility results of them. And interesting, the quantum Monte Carlo results points to two values of J. One for the higher energy, the higher temperatures, this yellow cycle here, the value is 0.4 for higher temperatures. For lower temperatures, here, this red cube, the J value is 0.2. So we have our fitting of the experimental curve is better if we use two values of J, one for the higher temperature region, 0.4, and one for the low temperature region, 0.2. Here we present the experimental data and the Monte Carlo results in physical units. And the conclusion is the same. We have two values of J, one for lower temperatures and the other for higher temperatures. So we have take these values of J and our low and in our marginal excitations here, and have compared with the results of the authors, and the comparison is very good for the two higher bands here. The antiferromagnetic band, they estimate that the energy here has this value, this high energy band, and the flat band, there is this value of 9 milli-electron volts. To make the comparison better, we need the lower energy scales to compare the neutron scattering experiments with the excitations on the ferrimagnetic phase. They stop here at 6 milli-electron volts. And these, using the value of J that we have estimated here, this band is in an energy scale that is not shown here. To end the talk, I will talk about the closing of the 1/3 plateau. Notice that the 1/3 plateau increases as J take values, positive values, as we increase the J in this positive value region. They increase going to the Ising limit that has a plateau. But if we decrease the value of J in this negative range of values, the 1/3 plateau decreases. So, as asked by the referee, we expect that it's possible that this plateau closes here in some point. It's at some point we expect that this plateau closes here in the negative range of J. Well, there are two possibilities for this case. One of them is as we found, as we can have in ladder chains, the spin ladder and the zigzag spin ladder, is that this plateau closes only in the decoupled chain limit. The decoupling, for example, J1 here is 0, or this coupling is 0. We have two decoupled spin 1/2 chains, and they are gapless. The gap closes on if J1 is 0. For this case, there is a formula obtained by these two guys here, that for the gap, that is the inverse of the correlation length, with an exponent here that is exact, 2 above 3. Another case that's found in some anisotropic ferrimagnetic chains, here I put one example, is that this gap closes and the system goes to before the decoupling, if you want, and the system goes to a gapless phase with a power law decay of the correlations. In this case, we have a transition with a a fixed value of the magnetization, and we does have a Kosterlitz-Tauler transition with a formula for the gap closing that is exact to with specific exponent here. So we have these two scenarios to investigate. Oh, the first thing that we should do is to rescale the quantities to investigate this closing, because if we go to lower values of J2, lower than 1, the more important coupling becomes the J2, not more J1. That's the energy scale that we were using to normalize all the energy in our investigation. So the first thing is to rescale these the parameters, né, by J2, because this is the relevant scale here. The modulus, né, the longest of J2. Doing it, the 1/3 plateau take this behavior. Notice in particular that the plateau points to this limit, that's the decouplet chain, it's the couplet trimer limit. Notice that we have J2 negative, so these spin-on-half are in a ferromagnetic oriented, and if we in this case, if J2 is sufficiently negative, we will have spin 3 halves coupled by a renormalized coupling here. In particular, if J1 is 0, we will have spin 3 halves decoupled units here, and any value of the magnetic field will orient this spin 3 halves units. So if the gap closes only here in the decoupled spin 3 halves limit, we expect that this first scenario is occurring in our system. The second of the Kosterlitz-Tauler transition, we will have the gap, the plateau closing before the decoupled spin transmission limit. We will have a Kosterlitz-Tauler transition, and for the Kosterlitz-Tauler transition, exactly at this point, the exponent of in the gapless phase is given by 0.25. We know it. So these are the two scenarios that we have investigated. Here. We have considered the transverse spin correlation functions and have used a methodology that was successful in other cases. And what we found is that this value of the exponent, as we increase the value of J2, notice that the exponent do not cross the 0.25 line here. So down to the lowest values of of the parameter that we have investigated, we did not found the Kosterlitz-Tauler's transition, but the results points that the exponent asymptotically goes to 0.25, since we have a high degeneracy state here for J2 equal to infinity. After that, we have investigated the behavior of this gap, trying to see if this meets the formula of the zigzag chain transition. And for our surprise, our results, this line, black line here, is in good accordance with this formula here, with the expected exponent. So our results points that there is not a Kosterlitz-Tauler's transition. The system closes the gap only for J2 equal to minus infinite in the decoupled spin 3/2 trimers limit. In conclusion, for negative values of J and the singlet phase, the primer chain has a low energy behavior like that of the spin 1/2 chain. For positive values of J and the 1/3 plateau magnetization, the primer chain model is a very good description for the magnetic properties of this phosphate compound. The 1/3 plateau closes on for J2 equal to, it's not good, on for J2 equal to minus infinite. I will correct this one here. Thank you for your attention.
Thank you, René. So the section now is open for questions or comments. If you have any questions online, please raise your hands. And I have just a very short question, René, regarding that tiny small gaps that you found associated with edge states.
Sim.
So you think that if you do your DMG calculations using periodic boundary conditions, these would not appear?
Yes. They do not appear. It's a boundary effect. It's a boundary effect.
Okay. And a second question is related to your the fitting that you did of the susceptibility data, showing that the data is consistent with one value of J2 for high temperatures and another slightly different one for lower temperatures.
Yes.
Can we understand or can we think that this is a sign that maybe the exchange coupling is anisotropic in the compound, some degree of anisotropy?
Maybe. To understand it, it requires more experimental data that we cannot. And I don't have an example that similar to it.
Because I was thinking here that at high temperatures, all the couplings among all components would play a similar role, but at lower temperature,
Maybe
the exchange is larger along one direction.
Maybe. It's possible.
Okay.
It's possible. But Marcelo,
Yes.
interestingly, if we take the highest value of J here and try to fit and compare with the neutron experiment, the comparison is poorer than the one that by taking 0.2. So anyway, if we are in a given range of temperatures, if we use the correct value of J, the experimental results is okay. The fitting.
I see. I see. Andreas has a question for you.
Okay.
Please, Andreas.
Yes, thank you. Okay, first of all, very nice work. So it is maybe related to the previous one. So also related to the compounds. So I don't know the compound that you were worrying about so much. I know other compounds like azurate, ether, and there actually the dominant coupling is between the two gray dots, the exterior ones. It's very important. And so the question is, there are two questions. Do you have arguments not to include these couplings?
One moment, please. Professor Marcelo, close the microphone.
Sorry.
There is some echo.
Okay, I hope we got rid of the echo. So, you know, in compounds like azurite, you have a very important coupling between the two gray dots in your first transparency. And there are two questions. Do you have good arguments to neglect them for this lead compound that you're looking for? And if not, would it be possible to include them in the analysis?
Could you repeat, please, Professor? I'm not...
So in the coupling geometry, you have so there are certain compounds where you would have actually a very important exchange path between the two gray dots. So the one at the top and the bottom, you would have additional couplings. Of course, it's very difficult to extract lots of couplings.
Yes.
But the question is, do you have arguments why in this lead compound they should be absent? And if you don't have arguments, would you be able to include them?
Yes. Okay. I think that I understand. Notes the exchange pathway here. You are telling that there is some coupling between these two spins here.
There might be coupling there. It depends on the exchange geometry.
Yes.
How probably it is.
Yeah. Yes. In fact, to understand, to investigate the model in this experiment of neutron scattering, they have included a coupling here between these two spins. But they do not have made the complete the chain. They have analyzed, tried to fit the experimental data using only 3 spins, J1 with J1, J2, and another coupling between these two sides. So they have tried to understand the neutron scattering experiment with 3 spin 1/2. They have doing it. They have obtained these values here from this extra coupling, J1 prime, J1, and J1 prime, and it's very little compared to the values of J1 here. They are very little compared. But remember that it was making only three spins. They did it only with 3 spins.
Well, I guess the quality of the neutron scattering data is not that great. I guess it's photo samples, yeah? So one would probably need better neutron data. I have to say something. Okay. Anyway, thank you very much.
Thank you.
Any other question? So if not, let's thank Professor René again. And we'll now have the lunch break and return in 1 hour and 45 minutes at 2 o'clock local time. Thank you.
Valeu.
Parar a gravação. Tá meio fraca a internet, não sei se é esse cabo.
Não, não é o cabo não, porque